Hello once again. Well, in this video we're going to look at an example involving an absolute value function, and we are interested in the derivative of this absolute value function when x equals 0. Another way of thinking of it is, what is the slope of the tangent line to this curve when x is 0, at x equals 0? Well, I always like to get a visual of what's going on, and I always graph it. I always just to give me a ballpark of what this thing should look like. Okay, so this should not be a big surprise to you. We know that an absolute value function is this v thing, where this is kind of a sharp point. And so you might be tempted to say, well, at 0, right here, at 0, the derivative, or the tangent line, will have a slope of 0. Okay, and maybe that's true, maybe it's not. We're going to find out here in a minute, but that's probably going to be your initial guess if you haven't seen a problem like this before. Okay, so let's see if the derivative at 0 of this function really is 0. Okay, so up until this point we've been using this definition of the derivative, and this came from this picture. This picture should look familiar to you, where this is my change in y. Okay, in other words, f of x plus h minus f of x, and this is my run, which is just h. If I'm not going to go into the details of this construction, they are in the previous couple of videos, so you can go back there and take a look. Okay, so now this is obviously a different function. This is not our absolute value function. It's x squared rather, but the definition of the derivative still stands here. As I let h go to 0, notice how h is getting smaller and smaller. As h goes to 0, what's the derivative of this curve at 1 in this case? Notice that I'm fixing this point at 1, and I'm letting h get really close to 0. And if you look up here, this is our derivative calculation. It looks like that the derivative is 2. Okay, well, this type of a problem, in other words, this absolute value function, we could actually use this definition to calculate this if we wanted to. But this is actually a really good example to introduce a different definition. And that definition uses the exact same picture. It just uses different labels. So let's look at some different labels here. Okay, so you can see that I have this value of c. I've placed c at 1. And then I have this other value of x, and this is going to be my variable. This guy is going to be the guy that's moving. Okay, so now you can see that this red dot represents f of c. This green dot represents f of x. Therefore, this height is represented by, or I should say this line segment here is represented by f of x minus f of c. And then as well, this length right here is x minus c, and that represents our change in x. So the change in y over the change in x is right here. So what happens if we let x get really, really close to c? Okay, well, you can see that we get the same picture that was going on before. The labels are just different. Okay, so it's important to understand what we're letting go to what. In the previous example, we let h go to 0. In this example, or I should say in this construction, we're letting x get close to c. In other words, we're letting x get really close to the point where we're interested in the derivative. Okay, this is another way to think of the derivative, and let's write it out formally. Okay, we have the limit as x approaches c of f of x minus f of c all over x minus c. Okay, this derivative, this alternative form of this derivative, is again very good for finding derivatives at particular points. If I want to find just an ordinary derivative at any point, I would probably use this guy. But if I want to find a very specific derivative, as in this case, at 0, then this usually is the preferred method. So let's go ahead and evaluate this. We have the limit. As x approaches what? Where are we interested in? Remember, we're letting x approach the value that we're interested in the slope of that tangent line. And we're interested in the slope of that tangent line at 0. That's what f prime of 0 is. Okay, is f of x minus f of 0 all over x minus 0. Okay, so what is f of x? Well, f of x is just the absolute value of x. And f of 0, what's f of 0? F of 0 is just 0, so I don't even have to write anything. Over x. Okay, so here's our limit statement, a pretty basic problem on the surface. Okay, you may be tempted to use direct substitution at this point, but you'll quickly see that we get an indeterminate form. So anytime we get an indeterminate form, we have to use other techniques to evaluate it. Now let's recall when a limit actually exists. And a limit is going to exist if the limit from the right and from the left exist. That's a plus right there. Okay, so think about if you're getting really close to 0 from the right-hand side. Think about what types of numbers those are. Well, they're positive numbers. And if I just kind of think about plugging in positive numbers into here, I'm going to get back those same positive numbers. In other words, the absolute value of a positive number is the same number. So my numerator, I don't need to write the absolute value of x, it's just x. And my denominator is just x as well. Okay, so let's simplify this even further. What is x over x? This is just 1. And so we get, let's just rewrite this whole thing. This might be a little bit excessive. But we really get the limit as x goes to 0 at 1. And some of you might be thinking, well, how can you just do that? What if x was 0? Well, x isn't 0. Remember, we're approaching 0. We're getting close to 0. So this function here is the exact same function as this guy with the exception of maybe at the point 0. But remember, we don't care about what happens at 0. So what is this limit? What's the limit of a constant? Well, it's just the constant. So it looks like the right-handed limit is 1. What is the left-handed limit? Well, we're going to approach 0 this time from the left-hand side. And now if you think about these numbers that we're kind of numerically plugging in here in our heads, we could use our calculator to do that. I won't do that right now. But just think about, we're plugging in negative numbers into this thing. What is the result of taking the absolute value of a negative number? Well, it's the opposite. What do I mean by that? Well, think about it this way. This little exercise is worth doing, I think. If I plug in a 2, out comes the very same thing. If I plug in a 3, that's absolute value there, out comes the very same thing. That's why I was able to remove my absolute values over here, because whatever x was, I knew it was positive, so I'm going to get back the very thing that I plugged in. But if I get a negative inside of my absolute value signs, brackets, I don't get back negative 2, I get back the opposite of negative 2. Positive 2 is the opposite of this thing. Okay, another way to think of it is if you think of negative 2 as just some object in here, it's just some blob, okay, just some negative value. Well, what is the result of that? Well, the result of that is going to be the opposite of whatever that blob was. Well, what is that blob? Okay, that blob is simply negative 2. Okay, so what is the opposite of negative 2? Well, it's just positive 2. Okay, so I go through that to show you that the absolute value of x, if x is negative, is the opposite of our input. And I do all that. Some of you probably got that on the first go, but I do that and people think that this is a negative value. It's not a negative value because you remember that x is negative. This is saying the opposite of that. Well, what is negative x over positive x? And that is just negative 1. And that is our limit, our left-handed limit. Okay, well, what do you notice? you notice that the right-handed limit is 1, the left-handed limit is -1. What does that mean then? That means that this limit right here, doesn't exist. What does that mean? That means that this function doesn't have a derivative at 0. Okay, and I think I want to point this out, that we're continuous at 0. Okay, this is a continuous function even at 0. We're just not differentiable at 0. The derivative to the left of 0 we can see is -1. The derivative to the right is +1, but the derivative at 0 doesn't exist. Okay, so we can write, to be complete here, we could say f prime of 0 does not exist. Okay, there you go. There's an introduction to the alternative form of the derivative, which is very good at evaluating a derivative at a particular point. We'll see you around.